Good afternoon, everyone. My name is Sanjay Beru, and I am an assistant professor of physics, and I'm also associate faculty of CSRC, advising Antonio here. I am here, not introducing me, but I will introduce our speaker this afternoon, Professor Santosh KC. He joined early this fall, SDSU Mechanical Engineering Department. Before that, he was an assistant professor at San Jose State, and he completed, he did two postdoctoral research at UCSD and Operational Lab, and he did his PhD at University of Texas at Dallas. And his work is mostly density functional theory of materials and guiding how the material synthesis can be or the properties. We do experiments and we take a lot of help from density functional theory. And recently we collaborated on in one of our NSF mid-scale research infrastructure proposals where we wanted to build photonic qubits experimentally and the computationally qubits guiding us. Okay, with that, over to you.
Okay, thank you so much. Again, my name is Santosh KC. I'm in mechanical engineering. I'm a computational person, so computational material scientist. Today I'm going to talk about structure property relationship in materials. So how we can calculate structure and properties of materials. So it's about, first we'll understand the science of that, physics of materials. And then once we understand that relationship, we can tune that structure and properties for various applications. Okay, just to give you a brief background, I did my PhD at UT Dallas. At that time, I work on solid electrolytes for battery application, and then 3-5 semiconductors, and some 2D materials, surface and interface properties. And then I moved to Oak Ridge National Lab, where I work on oxides and magnetic materials. And in my second postdoc in UC Santa Barbara, I was working on transparent conducting oxides. And then I joined San Jose State as a faculty. Then I started continue working on similar materials. Okay, and then at San Diego State University, I'm also more focused on mainly two kinds of projects. One is lithium-ion battery, and the other one is 2D materials. Okay, so this gives you some overview of research area. Actually, you can see first two, my focus area and other interesting area. I can collaborate with other experimental groups, and I have some experience on collaborating in those materials. What I do is computational modeling and simulation. So that's why I have that HPC at the center, and others, these are the types of materials I use. Okay, so everyone knows about different length scale. So if you see this plot in the chart, you can see natural things and then man-made things, right, with different length scale, right? So you can see DNA, nanometer scale, and then if you see some ants, 5 millimeter, right? So you can see also those man-made things, right, in different scales. So while going into those different scales, right, their physics, their chemistry will be different. So we need different kind of simulations to get that reality, right? So and then since I'm in materials, design side. So what we do in materials is we have a structure and then properties, right? And there is, you can see processing. Processing will change the structure, and then if you change that structure, you have that, and you will change the properties, right? Once you have desired properties, you can make device and measure the performances. So they are interrelated, right? If your performance is not good in that device, then you need to work on properties, but to have that properties, you need to change the structure, right? And to get that structure, you need to do processing. Here is one example. So this is resistivity versus composition, right? So this is copper and gold, but if you can see the red dot, that's quench, right? When it is hot and you suddenly cool down, and that's the property you got. But if you anneal, slowly cooling, then you have that stress will be released in different phase, and then properties will be different. So even with the same material, by processing condition, you can have completely different properties, right? So in my research, what I do is mainly focus on structure and properties, right? Look into structure and understand details about its structure. Its structure can be atomic, crystal structure, like that, and then look into properties. And then when you design materials with different properties, we design that structure, right? By doping, for example, or creating defects. Okay, just to give you some idea here. So in left, we have diamond, right? Very shiny, expensive, the hardest material. And if you look into crystal structure, we'll have this kind of structure, right? So these are carbon atoms in this kind of coordination. If you look into single carbon, we have this cell model for that, right? And if you go into quantum mechanics, we have this kind of instead of having this deterministic orbits, we have this kind of probabilistic orbits, and we have orbitals. And electrons, they have also spin, right? So we can also take into account the spin of electrons. And now we know about this qubit system as well, right? So looking into different level, they have different structure. So we'll look into those structure and then properties, right? All right. So and in semiconductor industries, there is a law called Moore's law. It's not a physical law, right? It's what it says is like your number of transistors in microchips will double in every 2 years, right? So that's the trend we can see. But it has already reached the limitation, right? So you cannot go thinner than certain limit. There will be a lot of leakage. There will be issues with the device reliability and so on, right? So then new materials comes into play, right, to rescue that. Okay, and we know about, this is not the recent one, but what you can see here is supercomputer power, right? It's increased a lot, right? Okay, so we use computational resources to calculate those structure properties relationship, right? So since now we have those supercomputing facilities and software, we can compute those properties. Okay, so as I mentioned before, the length scale, right? At different length scale, we need to use different kind of approach, right? So for example, here, this is time scale, right? And this is system size. We use quantum mechanics, and as you go and larger system size, we have to use molecular dynamics or dislocation dynamics, measure scale, and other component actually device simulations, so on. So in this talk, I'll be more focused on density function theory and some molecular dynamics in this scale. Okay, so just to a lot of words here, but just to give you idea about everyone what is first principles approach, right? So we call also ab initio, that's from first principles. That's a Latin term meaning from the beginning, right? Starting from science, right? So if you have some equation, let's say Newton equation, whatever science equation, and based on that, no empirical parameters, no approximation, right? So, but of course, you'll see like it's not possible to do that, right? So, right. So we use we use this ab initio approach in understanding, designing, and then providing some guidance to the experiments. So so far there are two commonly used approaches like computational materials, right? Using those approaches, and then also instead of using individual, we have some kind of integrated computational materials engineering, right? Where you can use computational results and methods with experimental data, right? It's kind of feedback loop so that you can speed up and have realistic simulation. Okay, so for those accurate computation or realistic computation and interpretation, that requires knowledge, that knowledge of physics or chemistry, right? And then also experience. So it's something like some disease, right? So if there is some disease, there is no single medicine that can cure all of them, right? So you have to treat accordingly, right, based on that disease. Similarly, based on your material, based on the problem, we have to use different types of approximation. Okay, so what we use quantum mechanics, right? So I got this this words from this paper. So what it says, once we have this quantum mechanics, right? It solves everything, right? So you get total energy of the system, for example. So let's read here. So the underlying physical laws necessary for a mathematical theory of large part of physics and whole of chemistry are thus completely known. It's already known, right? We have that equation, Schrodinger equation, S psi equal to E psi, right? If you know Hamiltonian and wave function, you can completely solve it in theory, right? But what's the problem, right? So of course you can write that equation, but you cannot solve. The difficulty is that equation will be too complicated. So we have to use some, practical approximate, methods, right? All right. So that's what we do, right? So this method, this DFT density functional theory, is very popular and Nobel Prize winning method. So in 1998, Walter Kohn and John Pople received Nobel Prize in chemistry for developing this density functional theory in solids and also for molecules. So in real system, there are thousands of, actually millions of, atoms, electrons. So that, equations will be, huge, right? And then we need to solve that. So it's very difficult. Instead of, having that, trillion equations, we can convert that to, simpler, like single particle type of equations. And then all the properties will be function of electron density, right? I'm just trying to give you kind of hand-waving, kind of argument here, right? So this is electron density that depends on distance, right? X, Y, Z, right? So if you know electron density, you can calculate, let's say, energy of the system, right? For example, energy. So that energy that depends on density, right? So that's why it's functional, right? So it's like function of function, right? It's functional. Okay, we use those software packages. This is commercial and quantum space is freely available. We also use HPC resources. This is what I used before. And we're also working with the NSF Access to get allocations. So in DFT, that is, as I said, approximation solution to a Schrodinger equation, right? So we are solving those trillion, coordinate system, right? So so instead of using like many-body problem, right? So just to give you an idea, let's say you have a hydrogen, right? Hydrogen, you have proton and electron. Simple system. It can be exactly solved. But when you have, let's say, a bigger system, even atom, right, or molecules or solids, there's a many-body problem, right? You have electrons, right, many electrons, and then protons, right, and they interact, and they are not static, right? It's a dynamic correlation, right? Electrons are moving, so it's very difficult to solve exactly, right? That's why we need to do those kind of approximation. So Hamiltonian, right, kinetic term, potential term, right? And then what we do is use some approximation for that exchange correlation part. So For example, LDA, what we consider here is electron density is kind of constant, right, at different locations. And then in GGA, there is, instead of just having that electron density fixed, we have gradient so that we get distribution of electron density in the system. So these are main, we call it standard density functional, right? We use that, but if you see here, one of the basic theory, Hartree theory, and then LGA, GGA, and there are many functionals. As you go up, it's more accurate, right? But it's time consuming, it's expensive calculation. All right, so instead of using, for example, here we are using like a local density, right? Local, and in local plus, we have gradient of density. That's how it's going up, right? It becomes non-local here, and then we get more accurate results. Okay, so as I said before, it's not truly ab initio, right? Since we're going to use those approximation, and instead of using those, atomic potential, we use pseudo potential. It's not true potential, right? Why we use that is, let's say you have the big atom, right? So you have 4 electrons, protons, right? So that do not participate in chemical bonding, right? So what we can do is have all of them effective core, that potential, and outside we can have those valence, electrons, right? So that will give us the correct answers as well. So instead of using like all the electrons, so for some problems we have to use all electron potential, but many problems your pseudo potentials are good enough, right? Okay, so let's see some examples. So we can determine crystal structure. So we can calculate that energy as a function of distance, right? You are just minimizing that energy, and you can find out that binding energy, right? So your structure, right? This is example for, let's say, hydrogen molecule. So in principle, right, it's pretty similar for all solids, right? You change distance, you move atoms, and find out, track the energy, and find out the lowest energy, right? So, and then we do that for solids, and we can use Bragg's diffraction condition for different planes and find out those diffraction peaks, right? These are DFT simulated, and this is experiment. And once you have correct experiment, you can simulate this experiment patterns. So first we find the structures and then look into properties. This is the first step. We have to optimize the structure. So based on the material, we may have to use different functionals, right? So if you are layered materials, then you have to use, let's say, van der Waals function. So you have to add that dispersion correction, right? So, and if it is magnetic, then this standard DFT may not be enough, right? So in that case, we have to use some correction, right? So there is on-site Hubbard correction term. We can use that as well. And if it is strongly correlated, right? So we have to use that or beyond DFT approaches. Okay, so one example of properties, electronic properties. This is graphene, right? So this is band structure, energy versus K points. These are high symmetry K points based on the crystal structure, right? So you can see this cross here, we call this Dirac point, right? So it has metallic nature, right? So there is crossing of this bands. Okay, so let's see more properties. We can also look into lattice dynamics. So there are few methods. So one of them is we call density functional perturbation theory. Based on that, we can calculate those vibrational properties, right? This is frequency, and these are K points, right? So you can see acoustic and optical, right? So we can, and these lines calculated, and those, marks, the circles are experimental. So it perfectly matches with the experiment. Okay, so based on the symmetry of the crystal, we can also resolve those frequencies to IR active or Raman active. Okay, so what we can do using DFT, we can calculate total energy of the system. Right? We can predict crystal structure, calculate electronic band structure and density of states. And we can extract a lot of information from band structure as well, right? So if you are familiar, first thing is we can understand about its nature, right? It is a metal, semiconductor, insulator, or different types of other, let's say, topology of the system. And also we can extract mobility, right? Effective mass. The effective mass is given by the curvature of that bands, right? So we can also get those informations. And we can also calculate optical properties, absorption, and so on, right? We can calculate magnetic properties, diffusion coefficients, conductivity, right? We can create defects and see what's the role of defects on those electronic properties, optical properties, magnetic properties, and so on.
Can I ask you a question?
Yes, anytime.
So you have a Hamiltonian system, right? And I assume you're interested in conserving energy. Okay, when you solve your problem with your methods, do you conserve energy of the system? And also, what is the order of approximation with your method?
Okay, so what we do is get total energy of the system, calculate all those, kinetic energy, that electron, ion, all those, right? And then with respect to that configuration, and configuration will change, get energy, right? That's how we optimize, right? We get the lowest energy, lowest possible energy, right, to optimize that structure, right? It's not your energy is not, you are not fixing that. You are writing energy as a function of that configuration. Because this is the first thing you need to do, right? Because you need to optimize. That's directly based on that, constant that formulation, right? So if you really reach to the true ground state, right, and then that's the lowest energy, and your charge density will give us that, lowest energy. Okay, so once you optimize the structure, and then you can do this, self-consistent calculation in, let's say, electronic properties like that. All right, so and we also look into surface properties. We can calculate bulk, right? Crystal structure. We can create surface, and then calculate, surface reconstruction and surface absorption. For example, we can calculate work function, right? We can work on catalysis and lattice dynamics, which I just mentioned. We can look into polarization, piezoelectric properties, ferroelectric and multiplic properties, thermal conductivity, and topological properties. Okay, so these are some of the research that we did, right? And then, as I mentioned before, softwares, mainly we use this, and sometimes we may need beyond DFT. In that case, we use other softwares as well. And you can see there is a huge list of those quantum chemistry and solid state software. And you can compare which can calculate which properties. Okay, so that's the basic overview of the research method we do. Do you have any questions here? Too fast?
Well,
Yes.
I have another. I asked two questions and I didn't get any of them to answer.
Okay.
One was order of approximation. You're using a numerical method to approximate the solution to your system. What is the order of approximation that you get?
Okay, so for approximation, as I said, because if you use LDA, GGA, it's already there is approximation, right? But in terms of calculations, if you do like a SCF calculations, you want that accuracy, let's say in the next iteration, right? You have like a 10 to the power minus 6, like that kind of accuracy, right? You want to do that kind of accuracy. Did I answer?
Well, the order, you said first order scheme, second order, fourth order in terms of the error.
Okay, so there are two ways we get that error, right? One is if you compare with the experiment, right? The other one is how precise your calculations. It may be off, but how precise, right? So as I said, that precision is something like 10 to the power minus 50. You can pick what precision you want, right? 10 to the power minus 6. If you do phonon, you have to go higher, 10 to the power 10, that kind of precision. Otherwise, you get imaginary modes, some issues there. Yeah. You have a question?
I had a question about, you said you were able to calculate diffusion coefficients with DFT. Isn't that like a really small time scale though? So how are you able to get, are you using like ab initio molecular dynamics to get how it's moving through?
Yeah, that's a very good question. Yes. So if you use that in molecular dynamics, ab initio molecular dynamics, that time scale is very small, right? Picosecond, very small. So you cannot capture all detail, dynamics, but you can still get that, let's say diffusion coefficient, right? So maybe you can do on top of that, you can do some Monte Carlo type of calculations and get more realistic. But if you want to know just let's say diffusion barrier, right? So we can quickly calculate, right, as a function of temperature. Yes.
Can I ask about your inputs? Like, what are the limitations on what you can input into your system? Like, what kind of chemicals? What kind of you mentioned a lot about lattice parameters. So does it have to be in a lattice predefined to be able to import it into your system, or can you use more less homogeneous systems for
Okay. So yeah, what we need is structure information, right?
Okay.
That's it, right? It's structure, crystal structure.
So as
It
long
can
as
be
you know-
molecule. It can be molecule as well. So in case of molecule, the difference is far, right? We make a big box. They are far, right? So we use periodic boundary condition for solids, right? So if you use a big box and put molecule inside, you can calculate. What we need is just those position, all right? Position information. Yes. Any other questions? Yes.
I know you said some of the stuff is like approximated, or like it's hard to predict exactly. Do you ever use like any stochastic or like statistics-based methods to account for uncertainty, or do you only use like ODEs and stuff like that?
Yes. So we don't use that, but there are methods on top of DFT. Using those methods are there. Like in case of there is one stochastic GW, for example, anybody, they do those kind of calculations, but I don't do, right? Okay, so let's move on and give you some examples. So on 2D materials, right? So, okay, just to give you a brief idea, non-covalent interactions. So this, such as van der Waals interaction are ubiquitous everywhere, but it's poorly understood. So this is said, this is gecko on glass surface. It can climb up. It is said that those they have this large millions of villi, small. No, that there is that interaction will be like van der Waals like. So this is strong enough to hold that weight, right? So it's not true that van der Waals is weak. It's weak, but collectively it can be strong enough, right? So other examples, metal organic frameworks in batteries, layer materials, geolites, polymers, they have those kind of non-covalent interactions. So we can use DFT to calculate those properties. For that, we need to use a van der Waals interaction. On top of DFT, you have to take into account that long range correlation. Okay, so in 2D, I started with the graphene, right? It's Nobel Prize in 2010 for experiment regarding 2D materials. It's a wonderful material, right? So atomic thin, but for electronics, it cannot be used as a channel material, right? There is zero band gap, right? So, but there are other 2D materials they have sizable band gap and has a lot of applications, right? You can see some examples here. This is insulator, right? So this semiconductor, and some 2D materials, they have magnetic material there. So it's intrinsic magnetism is there. So it opens other applications, right? So magnetic electric device, information storage, 2D magnet, spin transistor, and so on. If it is not magnetic, right? So these are the potential applications. So you can see catalysis and lubricant is already available. So molybdenum is solid lubricant. So it's already available in the market. But these are potential applications. In future, we may have some devices based on those. Okay, so let's look into properties, structure and properties. There are layer materials. They are in plane strong covalent bond, and out of plane is weak van der Waals, right? So in that case, if you just take into account just the covalent, right? Just use the standard DFT like LDA, GGA, then calculate properties. This interlayer distance would be large, right? So it's not taking up on that in binding. So that's why we need to use van der Waals function, and we can get accurate structure. So if here moly and tungsten in group 6, right? And here is the sulfur, selenium, and tellurium. So they will have this kind of band structure, right? So if you have, if your combination is different, right, you can see how this, d orbital splitting happens. So we call this, crucial field splitting, right? So it makes here, you can see there is gap, right? Semiconducting, it's metallic here, right? It's semiconducting here, metallic. So based on that combination, we can have metal, semiconductor, even some superconducting properties are also discovered in those materials. Okay, so from Feynman, he was professor at Caltech. Maybe many of you already know. He says there is plenty of room at the bottom. Like if you go into that low dimension, there should be many opportunities, right, for physics, understanding, and also applications, right? So if you look into one of these material, for example, tantalum diselenide, for example, right? You can see it can be interconverted into different structure, right? So this hexagonal, right? S phase and there is T phase with a different temperature. We can create all, many of these phases, right? So the moly disulfide, it's right here. So you can see here, this is moly sulfur, and you can see sulfur. If you see from top, sulfur will be on top of metal, right? But if that is displayed, you can have many configurations like this. So what you can see here, a lot of structural variation. That means property variation, right? So that means that much more applications as well, right? So it keeps us busy in calculating structure and properties for various applications. So the other thing is it's a thin, right? Having like single layer. So its property will be different than bulk, right? So your electronic optical properties will be different, right? For example, it will be a larger band gap compared to the bulk, right? And its property also depends on where it is, like environment, right? If it sits on hafnium oxide, dielectric, so those, electron or electron interaction, that interaction will be screened by that dielectric. That means it will change that electronic and optical properties, right? So you can see the band gap is changed. It's like a freestanding and with this sanity structure. And that's what we published before. And then we can also create a heterostructure with other 2D materials for various device applications. In transistor, we'll have different interface, right? This is semiconductor here, and you have oxide, and you have metal, right? So you have metal semiconductor interface, oxide semiconductor interface. The nature of those interface will dictate this device properties, and we can calculate that looking into electronic properties like band offsets, band alignment, band offsets, and effective mass, mobility, and so on. And recently, people are also instead of just making like straight this kind of heterostructure, they are twisting. And by twisting, this is for graphing and HVN, you can see this kind of pattern, right? We call this Mori pattern, and that has some exotic electronic properties as well. Okay, so and then if we have iron or ferrous material, right? So if we have magnetic materials, it's more complication in terms of calculations because you need to take into account that magnetism as well. But there are more novel device applications as well. I'll give some example, simple example. So this is crystal structure of chromium chloride, trichloride, and you can calculate considering this non-magnetic without including those spin, right? Or you can make this ferromagnetic, or the spins align in one direction or opposite direction like this, and calculate total energy, right? So if you do, for example, if you, and then in that case, what you get is if you just use standard DFT, it says this is ferromagnetic is the most stable, right? But if you compare with the experiment, that's not true. Antiferromagnetic is stable. So since we have this magnetism, so we are not taking into account something there, right? That interaction. So if we use, for example, U, this is called Hubbard U, on-site Coulomb interaction fraction, then we can actually reproduce the stability as well as magnetic moments, right? And magnetic contribution, right? Everything will be correct. Also band gap will be also be correct, right? So as I said before, based on the material, we have to consider that physics. Some materials they have strong spin orbit coupling. We have to include that in our calculations. So if you don't include that, you don't get the right physics and right properties. Okay, so then we also want to know if this material can be cleavable to single layer, right? So we can just cleave that, right? So it's like exfoliation, right? So cleavage is like you have bulk and you create two surfaces, right? Cleave. Exfoliation is similar, but you are exfoliating top. You don't have material on top, right? You're removing one. Okay, so for example, if you cleave, and this is surface is the energy, right? Energy per meter square, and this is distance, and then you can see this is the cleavage energy, right? So if you compare this cleavage energy with graphene, so graphite different 4-3, so that means it's even easier than graphene to cleave, make it single layer. Okay, so this can be cleavable using standard mechanical exfoliation technique like viscosity. Okay, so what's the benefit? This is, you can see, this is insulator, there is a gap, right? And it's a magnetic, so you can use magnets to tune properties. And the other thing is when you flip a spin, it changes its lattice. So there is a spin lattice coupling effect. Okay, so more example, I think I'll skip this one. And then we also look into mechanical properties, right? This is new 2D materials, right? We have this structure. We also look thermal stability. This is using molecular dynamics. With their temperature, still the structure is stable, right? And then we can calculate phonon with a noise strain and applying a strain, and then it's still stable, right? We can look into electronic properties, clear band gap, right? With the strain, we can tune that band gap. So this structure is structurally, thermally, dynamically, and mechanically stable monolayer. So So using DFT, we can predict those properties. And so we can also create defects and see where are those defect level. So it may have various applications. Sometimes defects are desired, for example, in a quantum information area, right? So we can use those defects. So this is not the best material for quantum information, but similar technique we can use. And for semiconductor, we don't want, as a channel material, we don't want defect. In that case, we can do passivation. We can find out which species can passivate that defect, right? So we can remove that dangling bond. We also look into oxidation of the surface. For example, oxygen molecule comes in and absorbs here. What's the energy? What's the kinetics, right? So in this example, molybdisulfide, very high that kinetic barrier. That's why molybdisulfide is stable in air, right? But if there are defects, then it's a different story. So if there are sulfur packages, then oxygen will, absorb there easy. So, okay, we can also make alloys. We can mix different 2D materials and tune electronic properties, making metallic to semiconducting, open a gap, or if it's semiconducting, we can change the gap as well with a different composition. Okay, so how is time? Is it okay?
20 minutes max, I guess.
Okay,
You
good.
don't have to describe all your research. Leave some time for questions.
Okay, great. So in simulation, what we do is, our elements or compounds, right? We look into structure first and then properties, right? But now we work together with experiments and have that right kind of physics to simulate, right? We can have that kind of feedback loop, right? And then there are large set of database now, such as Materials Project, and but some kind of database is not very standard, like using like the same method for all kind of materials. Then I know it doesn't work for all of them, right? For example, actinides. If you are working on, half electron system, very localized, right? If you use just standard DFE, it fails to capture. So, but those data are improving, right? So, and we can also use machine learning to screen those materials, and then once we screen that material, we do like DFT. DFT is expensive than machine learning, right? And then we can go into details.
10 more minutes.
Yeah. Okay. So we can predict materials and then applications. Right? So we help, guide experimentalists. We also get feedback from experimentalists to revise our models. Okay. Quickly, I'll give you another example on ion conduction mechanism in solid-state battery. So everyone knows about how battery works. Three main components, right? Anode, cathode, and electrolytes. The conventional battery has liquid base, organic electrolytes. They have safety issues like catching fire and so on. It's organic, right? When it is hot, right, the organic material acts as a fuel, right? So what we want to remove that organic liquid-based electrolyte. We want everything solid. But the issue is any conductivity will be low, right? So we'll try to optimize that, right? So if you see battery technologies, lithium-ion battery has the highest energy density, right? So it's lighter and smaller compared to others. So we'll focus on this kind of battery. Okay, these are the issues, right? Solutions, there are multiple solutions. One is more like a battery management system where you monitor the health of each battery. Once it crosses some threshold of temperature, cut off that, use another one, like that. The next is use different materials, safer materials. So benefits of solid electrolytes, right? It can be thin, right? Safer, resistant to other external perturbations. Requirements: high lithium ion conductivity, low conductivity for anions and electrons. Electrons should not move, right? It will short circuit the device. Electrons should be outside, providing that current to be stable with electrodes. Okay, so these are some of the commonly used electrolytes. So what you can see here is stability, electrochemical stability versus ionic conductivity. So what we want is right here, high ionic conductivity and very stable. but none of them are there, right? So what we did, we look into this one, high ionic conductivity material, and dope that system and increase its stability. And the other way we did is try this one and try to increase conductivity. But we couldn't improve much this one, but we could do something here, right? Also quickly that one. Okay, so first in DFT, we need the structure, right? So these are the structures, and then we understand what's the ion conduction mechanism, how that lithium moves, right? In this example, lithium goes across this, right? So for example, this is ion conduction channel, right? In this case, like there are two kinds of lithium, two lithium sites. One is mobile, another is not, and it has 3D channel, right? It's complicated. And in this case, there are some places, here is lithium, there is vacancy. So the lithium goes to this vacancy site, and then lithium goes to other. It's like a vacancy. That means vacancy moves here, right? So it's a vacancy migration. So it has this lithium, it moves like this, right? It goes to here, and it creates some kind of dumbbell, like lithium dimer. So it's completely different, right? Here is different. So based on the structure, first we find out what's the conduction mechanism, what's the that diffusion pathway. Once we know that, we know how to align with the electrode, right? If it is G direction, then we'll align with the electrode, right? So we can do this kind of designing after understanding from first principle, right? DFT, using those packages, for barrier, we use noise elastic band method. We can use some molecular dynamics to get diffusion coefficients like this, right? We can calculate ionic conductivity after getting diffusion coefficient. Once you know the activation energy, right, we can get all this. Okay, so for battery, you can see this radar chart, or what you can see here is ionic conductivity. We want highest, right? So this system very high, but it's not cost effective. Mechanical properties is also not the best, right? And then stability is poor. So we are trying to push this, right? And so that it's useful. So what we think is, why expensive? Germanium is expensive, so we're going to replace with tin, right? And then sulfur, usually sulfurs are not very stable. Oxides are stable than sulfides. So we replace sulfur with oxygen with different composition. Okay, and we also look into other properties, mechanical properties. Okay, so this was done by my master's students at San Jose State. My germanium replaced with silicon and tin, cheaper, sulfur with oxygen. All right, and also sulfur with germanium with silicon. Okay, and then and also with a different composition, right? And also we also did replace phosphorus with antimony, right? So I'll show some examples. So with the tin, right? So and then it's ionic conductivity is also good, but pretty similar to the original one. We call that LGPS. This is the LGPS. High ionic conductor, we call this super ionic conductor, but not very stable. Right? Okay, so we calculate band structure. Right, so if you use the standard DFT, it underestimates the band gap. That's why we use hybrid functional. And we have this gap, it's insulator. Okay? Once you replace germanium with tin, band gap decreases. This electrolyte should be insulator, right? Its band gap should be large, right? So it's not good. So that will also restrict how thick you want to use. But if you replace sulfur with oxygen, you can recover. Actually, you can increase the band gap. Okay, but what about conductivity, right? So we can actually find out, optimize electronic properties and ionic conductivity somewhere here, right? You'll see there. Okay, for example, here, this is that migration barrier, the pure system. These are the dope system, right? So you can see if it is completely replaced sulfur by oxygen, large barrier. So conductivity decreases. It's not useful. So if you have some partial substitution, we can get relatively good ion conductivity. Okay, so using molecular dynamics, you can compute conductivity as a function of temperature, for example. Okay, so and then we also look into mechanical properties based on the structure, crystal structure, right? We know how many independent elastic constants there will be. We can compute all of them. And after that, we can calculate all the mechanical properties, right? Bulk modulus, Young's modulus, Poisson ratio, and so on. Okay, so why mechanical properties? Since in those materials, lithium insertion and extraction happens. In that case, electrolyte, also anode volume expansion and contraction happens. That will degrade the material. So, we can compute that from DFT. We can predict those elastic constants and compute all those mechanical properties. For example, here. So normally, if your fracture toughness is more than 100 megapascal, that will avoid that dendrite formation. That lithium actually can grow inside and make short circuit of device, so it will restrict that. Okay, so these are some examples. Just to summarize on this, right? So we look into electronic properties. We can also look into the phonon, and then once we look into electrolyte, we make interface and look ion conduction mechanism here. Okay, so that's not all, right? So through collaborations, we are also thinking to expand to multi-scale level, right? Not just the here, right? We are here pico nano region up to here, right? We are also expanding here with collaboration with Sarah and other people. So you can see we plan to actually go cell level and finally battery pack, right? So I'm not going to do that, but collaboration through collaboration we can do that. So all right. So consideration in simulation, right? We should understand the physics, right? Do we need a classical quantum and a scale, the dimension, experimental condition? You are simulating, let's say, freestanding in a vacuum, right? But in reality, you have some substrate there. Is there effect from substrate? You can directly compare, right? If your result from simulation exactly matches with the experiment, then something is wrong, right? Because you don't have same environment. It should give you some trend, some something close but not exact, right? So and some limitation, right? Level and how fast you run, and knowledge and experience is needed based on the material type, class of material, what kind of simulation we have to use, right? So there is one famous, modeling cow, right? For some application, it's enough. You can assume it's a spherical, and turns out it works. But some applications not, right? So, all right. So what next? Just to summarize, this computational material science plays critical role in designing next generation of semiconductor, energy storage, and other devices too, right? And nowadays, because of large data set, people are using like machine learning to train that data and predict properties, right? So, and then the next quantum computing. So using quantum computers to accelerate this material simulation is also underway, but it will take time, right? Not only that, materials for quantum computing as well, right? So quantum information science as well. We can use, for example, defects in wide bandgap semiconductor for the quantum applications. So that we're gonna collaborate with Sanjay on that area. Okay, so there are many resources available that we can use to predict materials modeling. Okay, so continuous advancements in computational power and algorithm development will accelerate this material state discovery. I think I will stop here and take any questions you have. Yes.
For the band wall materials, you use the band wall functional. So that is functional with like the explicit non-local correlation. Is that
Okay, yeah. That's a very good question. So there are different versions of van der Waals, right? Probably you are familiar with, Grimes approach, D2, D3,
Yeah.
right? But when you have spin, in that case, that's not exactly capture, right? When you have, it's like you need to capture this dynamic correlation with the spin, right? In that case, we use another one, PDW, right? PDWDF, that can capture.
That available in like a boss.
It was not before, right? I don't know. It may be in latest, but in Quantum Espresso, you can include that, right? So you can download that package and patch it and do that. That's what I did. Yeah.
And for the second project, I think we used the HSE functional. That is like a hybrid range separate, right? So that for that functional, is that supported by VASP, or you also need to use on Espresso?
Okay, so VASP, right? It's there. So you just need to change that. How much you want, like exact exchange, right? So let's say 25% you can get, right, exact like RT, and then you can get another from PB type. So you can do that.
Right. Okay.
Yes.
I noticed that you said you used nudge elastic band methods
Yeah.
for the second project. Was that just for like the lithium that's jumping between the vacancy sites?
Right. So to get that migration barrier,
Yeah.
right, we're gonna
NEB methods?
yeah, NEB we
Okay.
use. Yeah. The kinetics, right? For kinetics, we need. Okay. Any other questions? Yes.
Early on in your talk, you were addressing the integrated computational materials engineering, that being the combination of conducting computational examinations along with actual experiments to see if there would be additional results in application. I was curious throughout the work that you're doing, if these more physical experiments have been something that has helped supplement the computations that you've shown us, and if you might have interest, if anything concrete in terms of how these computational examinations you conducted could help also in turn supplement the physical experiments and eventual applications of the materials you're looking at.
Mhm. Yeah, definitely. So we need to always like benchmark, right, your calculation. So always compare the experiment available resources. So and in industries nowadays, they are using this integrated approach. In that case, you have computational data. Sometimes you don't need to, for example, you don't need to optimize the structure. If you know very good structure information, use that and compute properties, right? But if there is new material, then you have to find out, right? You have to test all those, as optimization. Yes. Yes.
Right.
Yes.
Oh, me, yeah, kind of a dumb question, but, I didn't really get, what informs your decision on how you modify lithium, molecule, optimize the conductivity and the stability?
So I don't know if I catch your question. For this lithium, what's your
No,
question?
I think it was maybe the slide. Oh, yeah, I think
Okay.
that, no, sorry, the top left diagram, like, how do you know what part of the molecule to modify to try to optimize? Like, what informs your decision? Is it like data or is it
Okay.
simulation or what?
Right. So the first thing we try to find out what's the mechanism, like how the diffusion happens, right? For example, if I check this one, there is lithium, there is vacancy. So it goes through this bottleneck right here, right? So the size will determine. So if you replace this with a different size, you can play with that port, that right, and that will change. So we go into that kind of details, right? You have titanium there, if you replace with zirconium, right? Then that will change that conductivity. So we can compute that migration barrier.
Yeah,
How to,
computationally, or do you have to actually like build that molecule?
oh, this one, the structure, right? These are just the numbers, right? Position. You can replace And then you have potential. You have lithium potential, right? If you want sodium, if you, in that site, you provide sodium potential, it becomes sodium. Right?
So this is completely given by the theory.
Yeah, completely in computer. You can design this all in computer, right?
Or you can like test a bunch of different combinations.
So you,
Or do you already know beforehand what's gonna happen if you use different?
so, okay, so sometime you can expect, right? So, but sometime no, right? For example, one example, right? Nickel and chromium, if you mix, the resistivity completely changes, right? So you cannot guess that until you do that, right? In some cases, there might be some kind of linear, so it depends, right?
But how, like, what is the cost, like computation?
Computational cost, okay. So if you do like DFT, very accurate, like it's costly, right? It takes time, right? Some calculations. For example, this one, it was close to 300 atoms. And this calculation optimization took something like a half month using like a supercomputer, right? So it depends.
On those supercomputers, they always have the 2-day limit. How do you run the job for half a month?
Yeah, so in that case, you know, this was done before, like I was working on national lab. Yeah.
That node, I think we're gonna